Okay, so here we go, continuity. What is continuity? Just a, it means like something unbroken, like, it doesn't have any breaks in it. Here's the definition of when f is continuous at a number. We have a limit at that number, and the limit equals the function value. Okay, what is that? So there's three things that are in that definition right now. F is defined at that number, okay, it has a value at that number. F has a limit at that number, and the limit equals the function value. The limit is the same as the function value. Okay, so here we go. It says, can you think of a function that's continuous at every number at interval? All kinds of functions are continuous, basically. If you look at the function, you can just assume they're continuous. Functions like polynomials, certain trig functions like sine and cosine, exponential functions, log functions are continuous. I should say log functions are continuous on their domain. Rational functions are continuous on their domain. And so, in other words, they have no holes, no breaks. All right. But sometimes it's a matter of pointing out when a function is not continuous. So what about this function here? Where is it not continuous? What's the first value as you go from left to right? What's the first number where it's not continuous?
3.
Before that?
1.
Do we see a little hole there at 1? Yeah. So, I know. You're way over there. Okay, yes, there's a hole there. So it's not continuous at 1. And this is a certain type of discontinuity called I'm just going to say removable discontinuity. It's a big word. Okay, and next number it's not continuous at?
3.
Yes. And this, where it's got two different limits, right? This is called a jump discontinuity, okay? The function kind of jumped. Yeah, from -1 up to whatever it is. And then another here, right? At 5, another removable discontinuity. Okay. Okay, and then as you look, maybe not even at the graph, it says, can you tell basically if a function is going to be discontinuous at a number? Well, let's look at this one. And the key here is to be able to factor this top part. Tell me what it factors into. I'm hoping to...
X minus 2,
x minus 2, x
x plus 1.
plus 1. Does that sound good? And of course, you got x minus 2 here and here, right? So you got a common factor of x minus 2. So does anyone know what that creates on a graph? If you have a hole, very good. Yes, when you have that common factor, top and bottom, creates a hole in the graph at 2. So there it is, a hole in the graph at 2. Gotcha. So letter B. This is I'll just graph this function. Okay, this is a function that goes to infinity on both sides of 0, both sides. So we say this is an infinite discontinuity. That's the third type of discontinuity. So we got a removable, a jump, and an infinite discontinuity. Okay, at 0. And then, okay, so and then this function, letter C, is the same as A, but f is defined elsewhere, basically at 1. So there's a hole, but there's a dot somewhere else. It's still discontinuous. And then where are each of the, okay, letter D, f of x equals x, that's that 45-degree angle line. And this is basically never, it's not discontinuous. So. Anyways, and so there's the example of A with the hole in it. There's the example of B with the infinite discontinuity. And do we see graphs for C and D? Nope. I don't see them yet. Oh, here they are. Oh, here's something else. Yeah, it's funny. This was meant to do this. I believe this is a typo. That's what it, yeah, that's what's missing. Okay, so does anyone remember this function? Or this is called the greatest integer function when I put those little double brackets around. No? Okay, well, I'll show you on the graph, this letter D. It's right here. Okay. What is that, the greatest integer? Basically, if a value of x is like 2.4, the function says 2. If it's 3.1, the function says 3. Okay, it stays at the integer value until x jumps up. Okay, so this function is also known as the birthday function because what do we do with our age function? Okay, what do we do with our age? We're the same age for a whole year, and then we, boom, jump up on our birthday, right? That's what happens with our age. Yeah, that's how we talk about it. And then they're talking about the different types of discontinuity, infinite. There's the 3 types, removable, infinite, and jump. Yeah. And then it says it could be continuous from the right as it approaches the number, no breaks, or continuous from the left. So it could be continuous on one side, or it could be continuous on an interval around the number. And if f and g are 2 continuous functions, then the sum and the difference, you can multiply, divide, all these things, you will still get a continuous function. And so we rely on that as long as g is not 0. And now they're saying there's special functions like a polynomial function. If you see a polynomial function, you can just assume it's continuous everywhere, all real numbers. And then a rational function is continuous where it's defined. So it might have some breaks in the domain, but it's continuous everywhere else. And all these functions, and these are the function we do calculus with, right? And so it's important for us to be able to assume continuity a lot of the time. In fact, here's a biggie. When you do a composition function, you put one function inside the other, you can assume, and both f and g are continuous, then the composition function is continuous. And that's going to happen a lot. And the last thing here that we're dealing with is called the intermediate value theorem, okay? And basically it says that if you have, and I'm going to draw a picture here. Here it is. If a function is down here at A and up here at B, okay, the y value is down, and see this pink line here? If the y value is below the pink line at A and above the pink line at B, then between A and B, the y value's got to cross. The function's got to cross the pink line, right? That's what it's saying. And if it's continuous, then we know it doesn't have any holes in it, so it's got to cross the line. It can't jump over the line. And in fact, it could cross, more than once, that line, not just once. And then if it's above the pink line here and below the pink line, again, if it's continuous, we know it's got to cross the pink line at least once. That's all it's saying. So we're going to have one of our worksheet problems is going to be on this. And then, just another, if you graph a function, you can see it in the window there. And I think that's it for our little presentation, and it's time for your break. So I'll see you back here at 11:02 at the latest.